be here to share with you my recent research results. The work I'm going to share with you is a novel approach for attitude estimation using MEMS inertial sensors. My talk today has the following 4 parts. Firstly, I will briefly introduce the backgrounds. Then I will show you the proposed method. The next is our experimental results. And finally, I will draw some conclusions. Okay, why we need attitude estimation? Because it's crucial for different types of robotic systems of their navigation and successful control, like UAV, mobile robots, and underwater vehicles, and etc. And MEMS inertial sensors is widely used due to its low cost, low weight, and small size. Here, I will share with you some of the fundamentals of the attitude estimation so that we can all stay on the same page. The Euler angles is usually is common to represent the attitude, like the yaw, the pitch, and the roll. And the rotation matrix here can be directly derived from these 3 Euler angles. And from the rigid body dynamics, we can calculate the rate of the Euler angles directly from the rate of the body terms. And the later one can be directly measured by MEMS gyroscope. However, gyros, which is slow time varying, would cause errors, especially in long-term application. So, most of the researchers are combining other sensors to improve accuracy, such as accelerometers, magnetometers, and GPS, and etc. And the first one, accelerometers, is very commonly used since our inertial measurement units products usually integrate 3-axis gyros and 3-axis accelerometers. And there are 2 of the 3 Euler angles, the roll angle and the pitch angle, can be calculated directly from the measurement of the 3-axis accelerometers by this equation. However, data from accelerometers provides no information of the heading angles. So, we need external sensors to provide information about the heading angles. But these external sensors would be hidden by environments such as GPS is not reliable or available in indoor environments, or magnetometers will be affected by steel structure nearby. So, as a matter of fact, Mahoney in 2009 theoretically illustrated when only a single measurement as the accelerometer's measurement is made in the body fixed frame of a constant reference, the system is unobservable. So our problem or our question is this: can we just use only the inertial reference, that is gyroscope and and accelerometers, to correct the heading angles without incorporating additional sensors, which is unreliable in a lot of environments? The next few slides, I will show you our proposed method. First, let's take a look back at the equations I mentioned. So there are 3 Euler angles rates, and the first 2 can be corrected by accelerometers. But the third one, the yaw heading angle, cannot be corrected. So from these 2 formulations, we can get the equation that has the relationship between the bias and the error that we can correct using accelerometers. But here we have only two values on the left, but we have 3 bias on the right to calculate, so it's unsolvable. But when we rotate the body, the IMU, under another orientation, we can get another equation like this. VK is different because the orientation has changed. So the bias is solvable under this circumstance where multiple orientations can be applied. So this is our method with the rotation of inertial measurement unit. We rotate the IMU around a rotation axis, and the IMU can get two different orientations. This rotation is actively rotating, which is independent from the rigid body motion itself. So we can get multiple orientations all by ourselves. Here, to improve the estimation accuracy, we're incorporating a complementary filter, which is commonly used in attitude estimation. First, we have actually 6 inputs, which have 3 gyroscope measurements and 3 accelerometers measurements. And then we combine their measurements and get their difference. Then estimate the bias. And with the rotation axis and the rotation angle, we can get the final attitude matrix of the rigid body. Here's the dynamics. And this filter has a converge condition where the gravity vector x over the last page is sufficient to reach, which is not a constant direction, specifying this equation. In a common sense, it's like when you rotate the IMU, the gravity vector is different when the inertial frame is rotating. So our method can apply to this converge condition. So here's the result. We can ensure the vector direction is permanently varying in a body fixed frame. Next, I will show the experimental results. This is our experimental setup. The industrial robot used to generate the motion of the IMU, and there's a rotation mechanism that are used to active rotate the IMU itself. So this graphic shows the gyro bias estimation results. The blue line is the ground truth, and the red line is the estimated bias. As we can see here, the red one, the estimated bias is very close to the ground truth, and within like no more than 3 degrees per hour. And this is the attitude estimated results when we compensate the gyro bias, when we correct the gyro bias. The red one is after we correct the Euler angles. Specifically here is the heading error. It shows the effectiveness of our proposed method. So here's the conclusion. We propose a new method for attitude estimation, use only MEMS gyroscope and accelerometers, which can provide heading correction. And this method shows good potential, especially for long-term navigation. Use only low-cost MEMS inertial sensors, especially in the case that when GPS, compass, and other external aiding sensors are infeasible. But our methods have some limitation. This method would lose effectiveness when the rotation axis is parallel to the gravity vector. In this circumstance, this rotation cannot generate new orientations and cannot make the gravity vector different in the body fixed frame. but it's easier to overcome this problem because when we use it like in mobile robots, we can like fix the rotation on a like not parallel to the gravity vector. It's easy to overcome in real applications. And our future work here is first to reduce the size of the system because we have a rotation mechanism, and improve the short-term estimation accuracy. Because when we use accelerometers, the signals will be complicated under high accelerations. Like in UAV, the acceleration is quite large. But this work has been done from many researchers. I think it's easy to overcome this problem. So this is my presentation. Thank you so much.